Hello Chem 1B, this is chapter 22, lecture video 4, and we're going to be talking about structure and isomerization in this lecture video. Isomers are defined as compounds that have the same general formula. So if we look at two compounds, they might have the same molecular formula, but they might be different from each other in one of two ways. So there are actually two types of isomerization in coordination compounds, and that is structural isomerization, or structural isomers, and this occurs when the atoms are actually connected to each other differently. Whereas in stereoisomerization, things are connected in the same way, but they have different spatial arrangements, meaning they, with respect to each other, are different in space, like around the structure. Now, a good example of a structural isomer is C2H6O. There are actually two structural isomers you can draw that have the same exact molecular formula. And that is, if we look at one version of this compound, looks something like this. And this is ethanol. This is the molecule in alcoholic beverages that is the alcohol part of alcoholic beverages. It has 2 carbons, 6 hydrogens, and 1 oxygen. Another structure also has 2 carbons, 6 hydrogens, and 1 oxygen. And it looks like this. And so this compound is known as dimethyl ether. And it is not healthy to drink. You would get very sick if you drank it, unlike this guy, which, I mean, if you drink too much of the ethanol, it'll get you sick too, but this could kill you. Notice they both have 2 carbons, 6 hydrogens, and 1 oxygen. These are structural isomers. An example of spatial isomers can also be done with organic compounds as well. Something like this. This is known as a trans isomer. Another example, the isomer that kind of corresponds to this looks something like this. Notice all the hydrogens and chlorines are connected to the same stuff, but their spatial arrangements have changed, and these are stereoisomers. Now, these are organic chemistry examples. Let's talk about some coordination compound examples. So with structural isomers, there are two major types of structural isomers that we can talk about when we're looking at coordination compounds. And they are coordination isomers and another one. We'll talk about coordination isomers first. So coordination isomers are when a ligand and a counterion switch places. So for instance, if we look at this compound, this doesn't really tell us what's in the complex ion and what's not. We could have actually a couple different options here. For instance, this molecular formula could be this, where we have the Br attached to the cobalt via a coordination covalent bond, and the Cl as an ionic interaction. But the Cl and the Br can switch places, like over here. Now the Cl is attached to the cobalt via a coordinate covalent bond, and the Br is attached via ionic. So these are two different compounds. They are very different from each other, but they are, as far as what's present in the compound, the same. Both of these have 5 NH3s, 1 Br, and 1 Cl. They both have 1 cobalt. So let's talk about linkage isomers. Linkage isomers are where our ligands coordinate to the metal in a different way. So for instance, it attached in one way in one case and in a different way in another case, but it's the same ligand. Example, nitrite ion. It can bond, actually, if we look at the Lewis structure of NO2. NO2 has a total of 5 valence electrons here, 12 there, plus 1 for the negative charge. This gives me a total of 18 valence electrons. And so I know I need to connect them with the O's and then go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 plus 4 is 14, plus another 2 is 16. We need to put our 2 there. Hey, look at that. But we don't have an octet on the nitrogen, so pick one of the options, erase a lone pair, add a double bond, and this is our Lewis structure for NO2-. Now, we can have one of these guys be shared with like a metal, let's say cobalt, and form a coordinate covalent bond there, or this guy could attach to cobalt and form a coordinate covalent bond there. Now the structure is going to be different depending on which one connects to our metal ion, right? For instance, if we have cobalt attached this way, it's cobalt attached to the O with 2 lone pairs, and then to the N, and then double bond O. This is one way of that ligand attaching. Another way is cobalt attaching to the N, which attaches to an O, which also attaches to another O. So these two ways of attaching are different, and this is a linkage isomer. There are a number of different linkage isomers that we need to be aware of. So we'll talk about them on the next slide. And they have different names, so you're going to have to know some names for some different linkage isomers, and I'm sorry, this, just like your polyatomics, is going to be a memorization type thing. Sorry about that. So again, now how do we know which one it is? Sometimes they're written differently, like this one is the O attaching to the cobalt. Sometimes they're written like this. This would be the N attaching to the cobalt. A lot of times what actually is going to happen is the element that is bonded to the metal is underlined. So something like this would tell us, hey, the O is the one bonded to it because it's the one with an underline under it. Okay, there are 4 linkage isomers that I need you to know. The first one is one we already discussed, and that is nitrito or nitro, right? NO2- has 2 different linkage isomers. One where we're bonding from the N, which is called nitro, and you need to know that. And another, which is where we bond from the O, and that's nitrito. For cyanide, Cn-, we also have 2 possible connections, linkage isomers. And that is, one, when we're bonding from the C, this is called cyanido. And 2, when we're bonding from the N, and this is called isocyanido. Next, we have thiocyanate, which is SCN-. If you bond from the S, it's called thiocyanado. If you bond from the N, it's called isothiocyanado. And then finally, our last one that you need to be aware of is cyanate, is OCN-. And so if you bond from the O in cyanate, it would be cyanado. If you bond from the end in cyanate, it would be isocyanado. So let's do an example problem. Let's say we have this complex ion, and we want to name it both ways that could be possible. Let's say we had an underline under the S here. In this example, we need to name it as we normally would. We start with the alphabetical order, so we got amine here, so we'd write amine. We have 5 of them, so we'd write penta. Then we would start naming our other anion. Now, since it's bonding through the S, this is just thiocyanado. Then we're going to write the name of cobalt. It's a cation, so we just write cobalt. And then it's going to be 2+, because this is -1, and this is 0. So this must have been 2+ if we have an overall +1 charge. So this is the name of that one. Let's look at a different scenario. Maybe that wasn't what we had. maybe we had something else. Maybe we had that underline under the N instead. Well, in this scenario, our name is going to be different. It's still going to be pentamine, but this time it's going to be isothiocyanato, and then cobalt, 2-ion. So wherever the underline is tells you where it's connected, and you should have memorized what this name is versus this name for those other 4 ligands as well. All right, if you have questions, just let me know.